Using 2/2/0 copper conductors in parallel for each leg of the service entrance is permissible. When paralleling conductors, the ampacity of the parallel conductors equals the ampacity of a single conductor multiplied by the number of parallel conductors. In the scenario presented, the ampacity of 2/2/0 copper conductors in parallel would be 2 times 150 amps, equaling 300 amps. Considering this exceeds the 200 amp service amperage, the configuration is deemed acceptable. Green RHH wire can be remarked to indicate its use as a phase conductor. This involves removing the existing green insulation from the wire ends where connections are made to the load or panel board. Subsequently, the wire is wrapped with electrical tape of the appropriate color for the designated phase, such as black, red, or blue. The recommended loss design point for a service entrance is 5%. This specifies that the voltage drop along the service entrance conductors should not exceed 5% of the voltage at the service entrance point. This ensures the voltage at the load remains within the acceptable range for the connected equipment. To calculate voltage drop, employ the formula voltage drop equals conductor length multiplied by current multiplied by resistance. Where conductor length represents the length of the service entrance conductors in feet, current signifies the amperage of the service, and resistance denotes the resistance of the conductors in ohms per foot. The resistance of 2/0 copper wire is approximately 0.64 ohms per foot. Therefore, the voltage drop for a 250-foot service entrance with 200 amps of current would be calculated as follows. Voltage drop equals 250 feet multiplied by 200 amps multiplied by 0.64 ohms per foot, which equals 32 volts. This equates to 32 divided by 240 multiplied by 100, which equals a 13.3% voltage drop, exceeding the recommended 5% design point. Consequently, the initial configuration is deemed unacceptable. To mitigate voltage drop, options include increasing conductor size or reducing conductor length. Alternatively, employing 4/0 copper conductors in parallel with an approximate resistance of 0.48 ohms per foot would reduce the voltage drop. The revised calculation would be voltage drop equals 250 feet multiplied by 200 amps multiplied by 0.48 ohms per foot, equaling 24 volts. This translates to 24 divided by 240 multiplied by 100 equals a 10% voltage drop, aligning with the acceptable 5% design point. The National Electrical Code, or NEC, provides guidelines for electrical installations to ensure safety and proper functioning. When considering parallel conductors, it's crucial to adhere to NEC regulations. NEC Section 310.10. Each addresses requirements for conductors in parallel. Firstly, conductors must be the same length conductor material, circular mill area, insulation type, and be terminated in the same manner. Secondly, the minimum conductor size permitted for parallel installations is 1/0 American wire gauge, or AUG, or larger. Thirdly, the ampacity of each individual conductor must be derated according to NEC tables if more than 3 current carrying conductors are installed in a raceway or cable. Fourthly, the overcurrent protection device should be sized based on the adjusted ampacity of the parallel conductors, ensuring it does not exceed the conductor's rating. Fifthly, properly documenting the installation with clear labeling at each termination point is important. This identifies the conductors as being part of a parallel set. The NEC provides specifics for the allowable ampacities of conductors based on their size and insulation type. Table 310.16 in the NEC provides ampacity ratings for various conductors based on insulation type and temperature rating. For example, a 2/0 copper conductor with THHN insulation, rated for 90 degrees Celsius, has an ampacity of 175 amps. However, this ampacity may need to be adjusted based on ambient temperature or the number of conductors in a raceway. When adjusting for ambient temperature, NEC Table 310.15. B2. Provides correction factors. If the ambient temperature exceeds 30 degrees Celsius, the ampacity must be derated accordingly. Similarly, when installing multiple current-carrying conductors in a raceway or cable, the ampacity must be derivated based on the number of conductors. NEC Table 310.15. C1 provides adjustment factors for various numbers of conductors. For example, if there are 4 to 6 current-carrying conductors in a raceway, the ampacity must be derivated to 80% of its original value. Remarking green wire, while permitted by the NEC under certain conditions, requires careful consideration. NEC Section 250.119 allows using green insulated conductors for purposes other than equipment grounding under specific conditions. Firstly, the conductor must be larger than 6 AWG. Secondly, at the time of installation, the conductor must be permanently re-identified at each end and at every point where the conductor is accessible. This re-identification must be done with marking tape, paint, or other effective means. Thirdly, the re-identification must completely cover the existing green insulation. Fourthly, the color used for re-identification must be appropriate for the intended use of the conductor, such as black for a hot conductor or white for a neutral conductor. When remarking green wire, it's important to use high-quality electrical tape that is specifically designed for this purpose. The tape should be resistant to moisture, chemicals, and abrasion to ensure long-lasting re-identification. Additionally, the tape should be applied in multiple layers to completely cover the existing green insulation. Proper voltage drop calculations are essential for ensuring the safe and efficient operation of electrical equipment. Excessive voltage drop can lead to reduced equipment performance, overheating, and premature failure. The NEC recommends limiting voltage drop to no more than 3% for branch circuits and 5% for feeders. To minimize voltage drop, several factors should be considered. Firstly, selecting the appropriate conductor size is crucial. Larger conductors have lower resistance and therefore experience less voltage drop. Secondly, minimizing conductor length is also important. Shorter conductor runs result in less voltage drop. Thirdly, reducing the load current can also help to minimize voltage drop. This can be achieved by using more efficient equipment or by balancing the load across multiple circuits. Fourthly, using conductors with lower resistance, such as copper instead of aluminum, can also reduce voltage drop. Fifthly, ensuring proper connections is essential. Loose or corroded connections can increase resistance and contribute to voltage drop. The voltage drop calculation formula can be expressed in several forms depending on the available information. The most common formula, as previously mentioned, is voltage drop equals conductor length multiplied by current multiplied by resistance. However, other formulas may be used depending on the application. For single-phase circuits, the voltage drop can be calculated using the formula voltage drop equals 2 times K times current times length divided by circular mils, where K is a constant representing the direct current resistance of the conductor material, typically 12.9 ohms for copper and 21.2 ohms for aluminum. Current is the amperage flowing through the conductor, length is the one-way length of the conductor in feet, and circular mils is the cross-sectional area of the conductor in circular mils. For three-phase circuits, the voltage drop can be calculated using the formula voltage drop equals square root of 3 times K times current times length divided by circular mils. The variables in this formula are the same as those used for single-phase circuits. The circular mil area of a conductor can be found in NEC Chapter 9, Table 8. This table provides the circular mil area for various conductor sizes. Additionally, online calculators and software tools are available to assist with voltage drop calculations. These tools can simplify the calculation process and provide more accurate results. When performing voltage drop calculations, it's important to consider all relevant factors, including conductor size, conductor length, load current, conductor material, and ambient temperature. Neglecting any of these factors can lead to inaccurate results and potentially unsafe installations. Always consult the NEC and other applicable standards for specific requirements and guidelines. In addition to the voltage drop calculation itself, it's also important to consider the allowable voltage drop limits specified by the NEC and other standards. As previously mentioned, the NEC recommends limiting voltage drop to no more than 3% for branch circuits and 5% for feeders. However, some equipment manufacturers may specify more stringent voltage drop limits for their products. It's important to consult the equipment manufacturer's specifications to ensure that the voltage drop does not exceed the allowable limits. Exceeding the allowable voltage drop limits can lead to equipment malfunction, reduced performance, and premature failure. In some cases, it can also create a safety hazard. Therefore, it's essential to perform accurate voltage drop calculations and take appropriate measures to minimize voltage drop to within acceptable limits. When selecting conductors for a particular application, it's important to consider not only the ampacity of the conductors but also the voltage drop. In some cases, the conductor size required to meet the ampacity requirements may not be sufficient to meet the voltage drop requirements. In such cases, it may be necessary to increase the conductor size to reduce voltage drop to within acceptable limits. The cost of increasing the conductor size should be weighed against the potential benefits of reduced voltage drop, such as improved equipment performance and extended equipment life. In addition to increasing the conductor size, other methods can be used to reduce voltage drop. These methods include shortening the conductor length, reducing the load current, and using conductors with lower resistance. Shortening the conductor length can be achieved by relocating the equipment closer to the power source. Reducing the load current can be achieved by using more efficient equipment or by balancing the load across multiple circuits. Using conductors with lower resistance can be achieved by using copper conductors instead of aluminum conductors. Each of these methods has its own advantages and disadvantages, and the best method will depend on the specific application. When designing an electrical system, it's important to consider all of these factors and choose the most appropriate methods for minimizing voltage drop. Proper design and installation of electrical systems are essential for ensuring the safe and efficient operation of electrical equipment. By following the guidelines and recommendations provided by the NEC and other applicable standards, it's possible to create electrical systems that meet the needs of the application and provide reliable power for years to come. The NEC is a comprehensive set of standards that covers all aspects of electrical installations, from the selection of conductors to the installation of equipment. It's important to consult the NEC and other applicable standards to ensure that all electrical work is performed in a safe and compliant manner. Failure to comply with the NEC can result in fines, penalties, and even legal action. In addition to the NEC, other standards and guidelines may be applicable to specific types of electrical installations. For example, the National Fire Protection Association, or NFPA, publishes standards for fire protection and life safety. These standards may be applicable to electrical installations in buildings and other structures. It's important to be aware of all applicable standards and guidelines and to follow them carefully when performing electrical work. Proper planning and preparation are essential for successful electrical installations. Before starting any electrical work, it's important to develop a detailed plan that outlines the scope of the work, the materials and equipment that will be used, and the procedures that will be followed. The plan should also include a list of all applicable codes and standards. Once the plan has been developed, it's important to gather all of the necessary materials and equipment. This includes conductors, conduit boxes, fittings, and tools. It's also important to ensure that all of the materials and equipment are in good condition and that they meet the requirements of the applicable codes and standards. Before starting any electrical work, it's important to energize the circuit that will be worked on. This can be done by turning off the circuit breaker or removing the fuse that supplies power to the circuit. It's also important to test the circuit to ensure that it is de-energized before starting any work. Once the circuit has been de-energized, it's important to follow safe work practices to prevent electrical shock. This includes wearing appropriate personal protective equipment such as gloves and safety glasses. It's also important to avoid contact with energized parts of the circuit. After the electrical work has been completed, it's important to inspect the work to ensure that it has been performed correctly. This includes checking all connections to ensure that they are tight and secure. It's also important to test the circuit to ensure that it is functioning properly. If any problems are found, they should be corrected before the circuit is energized. Once the electrical work has been inspected and tested, the circuit can be re-energized. This should be done carefully and deliberately. It's important to observe the circuit for any signs of problems, such as smoke or sparks. If any problems are observed, the circuit should be de-energized immediately and the cause of the problem should be investigated. Electrical work can be dangerous if it is not performed properly. It's important to follow safe work practices and to comply with all applicable codes and standards. If you are not qualified to perform electrical work, you should hire a qualified electrician. A qualified electrician has the knowledge, skills, and experience to perform electrical work safely and correctly. Hiring a qualified electrician can help to ensure that your electrical system is safe and reliable.